So our second objective is all about the second fundamental theorem of calculus, which will give us a pain-free way of evaluating definite integrals. Definite integrals are supposed to give us a net area bounded by the curve in the x-axis. The first fundamental theorem of calculus established a way to find the derivative of a function based on a definite integral, and it also establishes the inverse relationship between differential and integral calculus. Okay, so this one is going to give us an easy way to evaluate a definite integral, and it has something to do with the picture that's going on here. Now, rather than me just spoon feeding it to you, let's do a little investigation, which is going to lead us right into what the fundamental theorem of calculus, the second one, is all about. Okay, and it starts off with a very simple question. Given f of x is equal to a half x squared plus 2x, we just want to find the derivative. That should be easy. We could probably do this in our sleep. So f prime of x is equal to, and I just use the power rule here, leapfrog that 2 down, cancel out with the 1/2, just get x, and then the derivative of 2x is just 2. There you go, easy. What was the point of all that? I'm sure that there is one. Wait for it. Okay, so now on example 7, given f prime of x is equal to x plus 2, we want to find f of x. Oh, that sounds like we're just basically working backwards here, right? If you have the derivative and you want the original function, you're anti-differentiating. You're taking the antiderivative. And now we wouldn't be able to get this exact function here that we started with unless we had an initial condition, a point that's on the original function, which would do, it's right here. It goes to the origin, f of 0 is 0. So we already know what the equation is, but let's just go through that process, shall we? Of course. Now, since this one has a prime mark, to find its antiderivative, we're just going to get rid of it and just call it f of x is equal to, taking the derivative, I subtract 1 from the exponent, taking the antiderivative, I'm going to add 1, so it's x squared, and then divide by that new exponent over 2, plus 2 times x, just increase the degree there by 1, and don't forget your plus c, the constant of integration, okay? And we can figure out what the c is very easily because all we have to do is plug in a 0 for our x's and then set that whole thing equal to 0. 0 is equal to 0 squared divided by 2, 0, plus 2 times 0, 0, plus c. And then we can see clearly that c is equal to 0. Who would have guessed? So rewriting our final function f of x is equal to x squared over 2 plus 2x. And congratulations, what you have just done is just gone in a complete circle there for some reason. All right, I'm going to come back over here because I've got a nice, neat little animation for us. We want to evaluate the definite integral from 2 to 4 of x plus 2 dx. Now, notice that x plus 2, that integral, that integrand that's inside the integral, that's the same thing as this f prime function, which was the derivative of the function that we started with back over here on example 6, right? Well, what shape does this make? I don't want to have to do a limit of a Riemann sum if I can get away with it. And this one is just going to make a geometric shape that we can easily find the area of. If I plug in a 2 here, I get 2 plus 2, I get a 4. Plug in a 4 here for the upper limit, I would get a 6. It's just a straight line that connects those two things. And it's just going to make a trapezoid. We can find the area of a trapezoid, right? Look at that. That was a very nice animation. I'll come back over here. And let's actually find that area and see if we can make some connections. All right, base 1 over on the left-hand side, we got a 4. Base 2 over here on the right-hand side, we have a 6. And our height is 2. So the value of this definite integral should be 1/2 sum of the bases times the height. The 2 and the half will cancel out, and I just get 10. So the area underneath that curve from 2 to 4 is 10. So let's see if we can connect these dots. There's got to be some sort of relationship between these two things. All right, so on this next example, hopefully this is the one where everything falls into place. We want to relate the value of that definite integral, which was a number, which was the area underneath that curve up above the x-axis, to the graph of the antiderivative, right? That's the antiderivative of this x plus 2. Well, here, let's go ahead and plot that graph there. I don't know. It doesn't seem like there's a connection, right? This is a number, or this is an area. It was just 10. What does 10 have to do with this graph? Does it have anything to do with this graph here? Well, let me lead you to it just a little bit easier. What about this 2 and this 4 from the limits of integration here? Of course, those could be points on our graph. Here, let's graph each one of those things. I'm going to first graph the 4. If I come up to 4 on my antiderivative graph, I get a 16 there, okay? And then let's do the same thing with the 2. Plot the 2 on that thing. Okay, and then we get a 6. So we got a 16 up here. We got a 6 down here. Wait a minute. 16 and 6. If I take the difference of those, 16 minus 6, I get 10. And 10 was exactly the area underneath the curve. And maybe that seems like a stretch to you, but essentially that's exactly what the second fundamental theorem of calculus is all about. In order to evaluate this definite integral very easily, all you have to do is find the antiderivative, and then you plug in your limits of integration, and then you subtract them. That's it. That's the fundamental theorem of calculus, or at least a part of it. It's the second part of it.